Good morning, students. Today we will do the second part of the sequential circuits, where we would see three different types of counters. So today's experiment will be jointly done by myself and Mr. Amit Chettai. So the three experiments, let me just broadly explain to you. The first one will be a mode 6 ripple up counter. We will be using 74S112, which we used in the previous experiment last week when we did the JK flip-flop and toggle flip-flop. We use this same. So this is a Schottky TTL flip-flop, therefore it's very fast. So what we will do is we will be using a manual clock or a slow clock, a 1 Hz clock, and a 7-segment LED display to show you how it kind of cycles through each and every state of the flip-flop. And finally, we would show you this particular ripple counter working at higher clock frequencies, and we want to show you the problem with the ripple counter. The second experiment will be a mode 6 synchronous down counter. This time we will be using a 74109. This is a positive edge triggered JK flip-flop. So once again we would, mind you, this is a synchronous counter and it's a down counter. And we would look at the problem statement and accordingly we will design it, and we will show you the final circuit diagram. Then we will test it with either a manual clock or a slow clock of 1 Hz, and the output will be connected to a 7-segment LED display so that you can see the states happening. Once again we will see this particular synchronous counter working at higher clock frequencies, and that way you will be able to see the advantage of a synchronous counter as opposed to a ripple counter. Finally, we will use a very popular decade counter, which is 7490, very commonly used. We would see two operations of this. The most common operation is what is called the BCD operation, or the binary coded decimal operation, where the outputs, these DCBA or the QD, QC, QB, QA outputs would correspond to 0, 0, 0, 0 all the way to 9. So 0 to 9, that's a BCD. But at the same time, this particular counter has been designed in a very nice way such that you can also get a symmetric divide by 10 operation, which you cannot get in the case of a BCD operation. So these two operations of this particular popular 7490 decade counter we will see. So once again, like all our digital experiments, you would remember that it's very convenient to use a logic probe circuit as opposed to a digital multimeter, because what you are interested in are levels, not whether it's high or low, not the exact voltage. So therefore a logic probe would give you a visual indication of whether the state is 0 or the state is 1. So we would continue to use a logic probe. We will also use a manual clock depending on the operation, or you might use a slow clock just to see how things work. So once again you might remember, in the manual clock we used nothing but a set reset flip-flop. Whenever we press the set switch, the Q output went high, and whenever we press the reset switch, the Q output went low. And this is what we use for testing the JK flip-flop. So this 74S112 JK flip-flop function table and the pinout or the connections are shown here. Now you might remember that JK flip-flops have what are called synchronous inputs. J and K are synchronous inputs. Why? Because these J and K, whatever you put there, would take effect only at the active clock edge. In the case of a 74S112, the active clock edge is the negative clock edge. Now similarly you also have what are called asynchronous inputs. In this particular flip-flop you have a preset bar and a clear bar input. So when you make a preset input low, output, the Q output will become 1. Similarly, when you make a clear input 0, the Q output will be 0. So we would use this particular one to do our ripple counter design. Now once again we would, so that you get a visual indication, we will use a 7447 BCD to 7 segment decoder along with a 7 segment LED display. So what you see here on the right side is the common anode 7 segment display. So you can see why it's called common anode, because you would see that all the anodes are connected together and connected to VCC. So the 7 segments going from A, B, C, D, E, F, G, all the 7 segments are connected to the respective the outputs of the 7447 7 segment decoder. And we would not be using it, but all 7 segment displays also have a decimal point, or what is called a DP, which we can use when you have a multiple display and you want to show a decimal. But this particular case we will not worry about it. Now let's look at the problem statement of our ripple up counter. So what we want is, we want to design a modulo 6 or a mod 6 ripple up counter using negative edge triggered JK flip-flops. Now it's good to remember that whenever you are talking about an up counter using a ripple kind of a scenario, or a ripple counter or an asynchronous counter, it's always convenient to start with 0, 0, 0 and go to whatever is the maximum count required. In our case, we are talking about a modulo 6. So you would have 6 stable states. So we would go all the way from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0 and 1, 0, 1. Now what happens is, automatically at the next clock you would go to the what is called the unstable state or the quasi-stable state, which is 1, 1, 0. So once this state comes, what we would do in a ripple counter or an asynchronous counter is, we would decode this particular one and clear it so that it comes back to again 0, and it goes on and on. So the way you do this is basically, we would connect, mind you, this is a negative edge triggered JK flip-flop. Therefore, to get an up counter, we need to connect the input clock to the flip-flop A clock input, and the output, the QA output, or the output of the first flip-flop or the A flip-flop, as the clock of the second flip-flop, which is the B flip-flop. And the same way, again the QB output or the B output is used as the clock of the third flip-flop or the C flip-flop, and outputs are taken as CBA or QC, QB, QA. So this is the way we would do it. Let me show you the circuit diagram. So once again, we have shown all the circuit diagrams how it works. So you can see that we are using 74S112 negative edge triggered, and you can see the Q connected, Q of the first flip-flop or the QA connected as a clock of the second flip-flop, the B flip-flop, and the B flip-flop's output QB connected as a clock of the next flip-flop. And you can see that the preset inputs are disabled by connecting a 1 to all of them, meaning they will not come into action. But look at the connection of this decoder. So what we have done is, B and C or QB and QC are connected to a NAND gate, and the NAND gate output is connected to the clear of all these 3 flip-flops. So what would happen is, as soon as both B and C becomes 1, the output will become 0. For all other cases, output will be high, which means for all cases other than when B and C are 1, this clear would be at a logical 1, which means clear will not be in operation. So therefore what would happen is, the stable state, during the stable state 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, all these stable states, this particular output of the 7400 will be high, because you can see that B and C are not 1 here. But as soon as the next state comes, automatically when it counts up, when 1, 1, 0 comes, you see that this condition is satisfied, B is equal to C is equal to 1. Therefore output will become 0, and being an asynchronous input, the clear input, all the flip-flops will be clear. That's the way it works. Now you might ask, what about state 1, 1, 1? So this particular state will not happen normally, because you see that as soon as state 6 or the state the equivalent of 6, 1, 1, 0 comes, we know that we are clearing it to 0. But this state can happen only at power on, because when you switch on the power, the flip-flop can take any state, anywhere from all zeros to all 1, all of them. So the probability is 1 by 8. So there is a possibility that when you switch on the power, the A, B, C flip-flops have 1, 1, 1 at the output. If that's the case, we know that once again B and C are 1, therefore it gets cleared. And then once it gets cleared, it will keep on doing what happens here. Now let's see how the mod 6 up ripple counter is implemented. So what we have here, you can see we have the ripple counter, and we also have the 7-segment decoder and the 7-segment display, and we also have here 4 logic probes put here, which would actually show you the actual state. So let's look at first the display. So you can see that it's cycling 3, 4, 5, 0. 1, 2, 3, 4, 5, 0. So you can see that it's going from 0 all the way to 5. We are not able to see the 6th, 6. Why? It comes for a very short time and it disappears. Once again, if you look at the logic probes, you can see it's cycling 4, 5, 0, 1, 2, 3, 4, 5, 0. So it keeps on going. Now what I want to show you now, so this is a 1 Hertz clock we have given. So that's why we are able to see the kind of slowly going, and a very nice way, or instead of using a manual clock, we are able to see it cycling through. Now let's have a look at the waveforms, what you would see on an oscilloscope.
Please note that all the waveforms are changing at the negative edge of the clock. So that's very important to notice.
So what we have done here is, on the oscilloscope, on the top you would see the clock, this is a 1 Hertz clock, and then you have here the A output, which is the LSB, and then you have the B output, and finally the C output. Mind you, this is a digital storage oscilloscope, therefore even though the frequency is only 1 Hertz, it has picked up nicely one of the problems I want to illustrate. So we know that, let's look at the states here. So you can see that, this is A and this is C. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, which is the last state, and before it goes to the next one, you can see a small kind of waveform you can see here, which is nothing but actually the state came and it disappeared. So once again you can see that as soon as 1, 0, 1 comes, at the very next clock, for a very small interval, the B output went high. You can see that here because the digital storage oscilloscope. What I want to show that is, now let me increase the frequency. Right now it's 1 Hertz. Let me make the frequency 1 megahertz, and let's see what we would see. So what we would see now is, let me just increase the frequency of the, let me go to 1 megahertz. Yeah, so right now the frequency is 1 megahertz, and now you are able to see this particular B output going high. So you can see once again same thing. So 1, 0, 1, which is state 5, and as soon as the B output goes to 1, 1, 0, you can see it went up and came down for a very short time. Right now unfortunately the frequency is 7. Let me just go to 1 megahertz. Yeah, at 1 megahertz you will be able to see it much better. Yeah, you can see this particular trigger here, which is happening here, which is exactly the. Now look at if you look at the waveform, right now what we have done is the voltage setting is 5 volts. You can see that this particular signal is going all the way, almost definitely more than, it has gone all the way high, and it's going all the way to almost about 3 plus volts. So therefore, in this can give you serious problem, which in time critical applications it can give you a problem. So therefore, it's commonly ripple counters are not used beyond a particular frequency. Let's say a few megahertz is not used. So right now we are talking about roughly about 2 megahertz, and you can see this is very prominently seen, which can create trouble. So in summary, we can say that ripple counter, what is the advantage? It's very easy to design. You saw that all that we did is we just needed one decoder. That's all we needed, and therefore it's very easy to design. What is the disadvantage? We saw that the ripple counters can be used only up to a few megahertz, and the maximum we could see is that let's say about 2 megahertz or a few megahertz. The outputs, why? Because the outputs are asynchronous outputs. Therefore, in several applications this may not work, especially wherever this quasi-stable state, in our case that state 110 came for a very short interval and then it disappeared. This can create trouble in time critical applications. Mind you, in this particular experiment we use 74S112. That's why it is so less, that instant for which it is high, that state 110, which you are able to see on the scope, is extremely small. But however it's there. But if you had used a slower gate like a 7 standard TTL or even an LS TTL, you would have seen that this particular that quasi-stable state, you would have seen it more clearly. So this is the disadvantage of using a ripple counter. Therefore, ripple counters are used where this kind of things are not important, especially when you are talking about a display, where the human interface, we will not be able to, we couldn't see this kind of a small quasi-stable state in our LED display. So that kind of applications ripple counters are used because it's very easy to design. Now let's look at the second part of the experiment. This time we would see a modulo 6 synchronous down counter. So let's first look at the problem statement. The problem statement is like this: design a modulo 6 synchronous down counter using positive edge triggered JK flip-flops with the following sequence of states: CBA 111, 110, 101, 100, 011, 010, and then back to 111 and so on. So you can see that 2 states are missing. So the unused state, and the problem statement also says if any of the unused states, that is the states 001 or 000 comes, the next state should be 111. So here the 2 major difference. One thing is this is a synchronous down counter, and also this time we are using a positive edge triggered JK flip-flop. Last time we were using negative edge triggered JK flip-flop. So all the outputs changed at the negative edge. This time all the outputs will change at the positive edge. So this being a synchronous counter, you need to design it. Let me not go through them in great detail, but let's quickly show you a few things. Number one, for designing a synchronous counter, the first thing you need to do is you need to write the transition table, which you arrive from the JK truth table or the function table. So here in a transition table, you have on the left side 2 entries, Qn and Qn plus 1, meaning the present state and the next state. Now to go from the first, if you look at the first entry, right now if it is 0 and the next state you want the Qn plus 1 you want to be 0, what should be J and K? And in this case it says J should be 0 but K can be 0 or 1 and so on. So therefore the way we do this, the design table, what we do is we first of all write at the extreme left 3 columns CBA corresponding with the states, and you write in the sequence or the sequence of states. So here we have written 111, 110, 101, 100, 011, 010, and then after 010 we want the counter to go back to 111. So therefore you have all the 6 states here. So 1, 2, 3, 4, 5, 6 states here. And at the same time, we also specified in the problem that if 0, 0, 1, which is an unused state, comes, the next state should be 1, 1, 1. And also, if the unused state 0, 0, 0 comes, the next state should be 1, 1, 1. These unused states can happen only at power on. But you need to design it such that there is no ambiguity in the design. So what you would do is you would use the transition table. For example, if you just look at the first entry, the first one is 1, 1, 1. Look at the C. Right now it's 1. The next state is 1. So Qn is 1. Qn plus is also 1. Therefore, here we find from the transition table that Jc can be x, which means 0 or 1, but Kc must be 0, and so on. Similarly, if you look at the corresponding one, 1, 1, 1, and the next state is 1, 1, 0, you see that in the A flip-flop, the Qn is 1 and the Qn plus 1 is 0. Therefore, you will look at what should be the case from going from 1 to 0. You see that it's x1. Therefore, here you are written corresponding to the A flip-flop is written x1, and so on. You write it up. Then you need to finally each of these entries, JC, KC, JB, KB, JA and K, each of them you need to have a 3 variable Carnot map, and the variables are CBA. And finally, after you do it, you would get these are the solutions. JA is 1, KA is C plus B, JB is C prime plus A prime or C bar plus A bar, and KB is C A prime, and JC is B prime plus A prime, and finally KC is B prime A prime. Now we have used a 74109 positive adjusted JK flip-flop. Now this is not a JK, this is a JK bar flip-flop. Now you might wonder why they have made a flip-flop like this. Now they have done it in such a way that if you want to use this as a D flip-flop, then what you need to do is you can just connect the J. Okay, if you want to use if you want to design a delay flip-flop using a JK flip-flop, what you would do is you would connect your D input to J, and you would use an inverter between that J and K. So exactly the same thing they have done here, so that you get a functionality. But unfortunately, this gives us trouble for our design. So let's look at the function table. First of all, you see that this is a positive edge triggered JK flip-flop. So therefore, all transitions occur at the positive edge. And just like 74S112, here also you have both synchronous inputs and asynchronous inputs. Synchronous inputs you have J and K bar. Asynchronous inputs you have preset bar and clear bar. So for normal operation, you need to keep both preset bar and clear bar as high. Only then the normal operation will happen. And otherwise the normal JK functions will happen, except that here it is JK bar. So finally, the circuit here drawn here. So the only difference is whatever K map final minimized functions you got there, you need to remember that instead of K, you need to this particular JK flip-flop, because you have a JK bar, you need to complement all of them. So I have written all of them in complement form, and you need to do that. So we have not given all the details there for the sake of simplicity. So this is what we have. So let's see how this particular synchronous counter is working. What I have done is I have given a manual clock from the function generator, and the clock is half hertz. Therefore, you would have much longer period to see. So right now you can see in this 7-segment display, and the output of the CBA outputs we are connected to the 7-segment decoder 7447 and a 7-segment display. So you can see this outputs here 7, 6, 5, 4, 3, 2, and then it goes back to 7. So you see that those states 0, 0, 1 or 1 and all 0, 0, 0 are missing. And what we have done in this logic probes is you can see the corresponding logical the binary output. So you can see here 5 correspond 101, 4 100, 3 011, 2 010, and 7 again 111, and so on. So this nicely works very well. So let me show you the waveforms here on the oscilloscope. So first thing to notice here is all the transitions. So what we have on the top is the clock waveform, input clock, and then you have the A flip-flop, then you have the B, then you have the C. So most important thing to notice here is you can see all the transitions are happening at the positive edge. All the flip-flops are changing at the positive edge. So you can see here, you can see basically all the states you can see here happening. So let me just show them one by one. So this particular one is 111. Let me choose a particular place. Maybe let me change the frequency, and then I can show you the. Let me go to about 1 megahertz, and let me then show you all these states properly. So I am going to use 1 megahertz as the clock frequency, and so you'll have much more stable case there. So so you can see here this particular case. You can see you can see this particular case. Or first of all the outputs change at the positive edge. So in this case you can see 1 1 1, which is 7, and next one 1 1 0, which is 6, 1 0 1, which is 5, 1 0 0, which is 4, 0 1 1, which is 3, 0 1 0, which is 2, and then again it goes back to 1 1 1. Now you can see that there is a slight between 7 and 6 there is a slight change, but important that don't get confused. As long as this particular state is above the voltage, which is the right now the setting is 5 volts. So you can see that that is not going to, so don't get confused with that. That is still high. That's the important thing. So it's working very well. Now one important thing to notice here is, let me, right now is 1 megahertz, let me increase the frequency, let me go higher. So let me go to 5 megahertz. And you can see that this ringing because of the wiring here, otherwise you can see the outputs are quite stable and steady. Let me now go to about 10 megahertz. Right now it's 10 megahertz, and you can see, unfortunately, because this ringing which you see is because of the wiring, so I am not supposed to do this much wires, I should not do, but otherwise you can see as far as the flip-flop is concerned, things are okay. Let me go back to now about 5 megahertz, and we saw that in the case of our ripple counter. Here the most important thing to notice here is you can see that all the output, there is, you don't find anything, any glitches or anything. But another very interesting thing is you can see all the states are changing at exactly at the same time. And mind you, we have this time used 74109, which is a standard TTL gate. And even with a standard TTL gate, I am getting a much better performance compared to a ripple counter where we use a Schottky TTL gate. I want to show you something that what will happen when the unused state happens. Right now let me give you the case of all zeros, because what we have said is if it is all zero, next state will be 7 or 111. Let's see it happening. Now what I am doing is I am clearing all the outputs together. So now it's 0. Let me just clear all the outputs together. Let me clear all the outputs. Okay, output is cleared now. Let me remove it. You see that it just becomes 7. Now next one, let me just do one thing. Let me now do the, so what we are doing now, the unused state 1, 001 or decimal equivalent 1 is there now, and let's see what will be the next state now. Next state is 7. So this is why we said, so all the cases now we have taken care of, including the unused state. So to summarize the synchronous counter, we saw that it worked very well for all that we designed for, including the unused states. And we also saw that the major advantage of a synchronous counter is that it can work up to the maximum rated frequency of operation of the flip-flop. Since we used a standard TTL for this particular application, it can go up to about 25 MHz provided you do a very proper wiring, and better still, you need to make a PCD. With low power Schottky TTL, you can go up to about 30 MHz, with a Schottky TTL up to about 80 MHz. But the major disadvantage, if you may say so, is that each counter needs to be designed as per the required sequence of states. And you could see that in the previous case, we had a fairly complicated kind of a design, but you need it only once. But the advantages you get are far more superior. Now we'll go to the third part, which is the 74990 BCD and Decade Counter. 7490 is a very popular decade counter. Decade meaning 10 divided by 10 counter. It's basically designed using 4 master slave JK flip-flops. Therefore important that when you look at the oscilloscope, you will see that all the outputs change at the negative edge because it's a master slave JK flip-flop. This particular IC 7490 is an interesting IC. Inside it has 2 sections. One is a mode 2 counter, other one is a mode 5 counter. Now because of this kind of connection, you have 2 modes of operation. The first mode is what is called a BCD mode or a BCD counter. This is for displaying decimal digits from 0 to 9. So that's the commonly used BCD counter. The second one is interesting, which is occasionally used, which they called a Bi-Quinary counter, meaning you would get a symmetrical divide by 10. Now you would appreciate that in the case of a BCD counter, if you take the D output or the QD output, you would see that it is high only for state 8 and 9, and for all the other states it is 0. Therefore, the output is not symmetric. Only for 2 clock states it is high, all the other states it is low. Whereas if you use this Bi-Quinary counter, what would happen is it's done in such a way that you would cascade the 2 and the 5, which we would show you how it is done. Now looking at the decade counter, both the pinouts and also the other details, you can see that on the right side, you can see that this is the inside diagram of the 7490 counter. There are 4 flip-flops here, and you can see here in the pinout, you can see there is an input A here. So that is the first mode 2 counter, input A and the QA. So this input A and QA constitutes the mode 2 counter, and you can see that there is an input B. So input B and the B, C, D outputs put together, it's a mode 5 counter. So by cascading these two, you get 2 kind of modes of operation. The other thing is, which you may not require, but it's just good to know, this has a very special feature by which you can either preset or clear it to all 0 or preset it to 9. So for example, if you keep, there are 4 pins, there's an R01 and an R02 which are meant for clearing it to 0, and an R91 and R92 which are meant to preset it to 9. So if you make the R91 and R92 high, irrespective of whatever is R01 and R02 input, you would see that your QD, QC, QB and QA will be high, low, low, high, or that is 1001, this is corresponding to 9. But if you want to clear it, then you need to keep R01 and R02 both high, and let's say if you keep both R9 and R91 and R92 low, then you would get all the output to be cleared. But for normal operation, it's safer to go for the last entry. You can keep all these 4 inputs, R01, R02, R91 and R92, all of them, if you keep it low, then it will work like the normal counter. Now let's see the first operation, which is the 7490, the BCD operation. Now you can see that you here on the right, the extreme left side, it's shown all the clock counts going from 0 to 9, and the corresponding QD, QC, QB and QA. And you can see that it goes from all zeros and it goes to 1001, which is 9. So the way, as we said, is the way it's connected is the clock is connected is the input clock is connected to input A, and your QA would give you the divide by 2 or the mod 2 output. So that QA divided by 2A is connected as a clock to input B, and therefore your BCD outputs will be now from DCBA or QD, QC, QB and QA. So essentially what you are doing is you are cascading mode 2 followed by mode 5. This is the normal BCD operation. So let's see its operation, how it is working. So what we have here is the BCD counter, and we are given a slow clock, a clock less than even 1 Hertz. So you can see that the 7-segment display is nicely cycling through all the decimal digits going from 0 to 9, and you can see that after 9 it comes down to 0 and it goes 0, 1, 2, 3 in that order. And here this green LEDs are the logic probes. You can see the corresponding to the 7-segment LED, the corresponding values you can see. So right now the 8, so this is 9 and all are off. So you can see 0001 and the 0010, 0011, 0100, 0101, 0110, 0111, 1000 and 1001. So it's we beautifully see. So what I want to show you now is let me increase the frequency to 1 megahertz, and let me show you the outputs, how they are coming. So you can see that one very important thing to notice here is you need to first of all look at the clock edges. So what we have right now on the top is the clock, and this is the A output, this is the B output and the C output. We can display only a maximum of 4 outputs here. So right now we are showing only the the clock and the A, B, C output. So you can see that most important, all the transitions are happening at the negative edge of the clock because it's a masslessly decorated clock. You can see that very well. And we don't have D here. So if you look at it carefully, you can see that we can start from here 0, 0, 0 you can see, and you can see 0, 0, 1, 0, 0, 0, 1 and then 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1, and the next time it will go into 0. That's the time the QD output will come. Let me right now change the QD. Instead of the clock, let me connect the QD, and let's look at all the, so you can see now all of them. So this is the QD output here, and you can see that corresponding to QD goes high. So this you can think of as 1, 0, 0, 0, and then the next time you have 1, 0, 0, 1, and after that QD becomes 0. So QD output will stay low for 8 clocks and it stays high for 2 clocks. So you can see that the output, the QD output, which is the divide by 10 output, you can see that it's not a symmetric output. So this is a operation of a BCD counter, and then this is working so well, and we are able to see this well as a BCD counter. So we come to the final part, which is the 7490, what is called the Bi-Quinary or symmetric divide by 10 operation. So what do we do here? So we said already that the 7490 has 2 sections inside. One is a mode 5 and a mode 2. The way you connect it decides whether it is a BCD or a Bi-Quinary. So in this particular case, Bi-Quinary or the symmetric divide by 10, what you do is you first use the mode 5 and follow it by a mode 2, which means the clock input you would first give it to the input B of the 7490, and your output you will take from QD, which will give you a divide by 5. And that divide by 5 output, then you feed it to the input A, which is the A flip-flop, and take output from the QA, which is the, then therefore what will happen is you would get A as the MSB, and the next higher one would be D, C, and B will be the LSB. So if you're looking at the Bi-Quinary, what you would get is, you can see that you would get outputs going from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. And then you can see again it is continuing, while the QA output, you can see that it goes 0 and goes high. So therefore it will be symmetric. Now if you look at the waveforms there, what we have shown here is the frequency we have put as 1 megahertz, and what you see here on the top is the clock frequency, and what you see the second waveform is the QA output, which is symmetric divided by 10. Now you can see that, look at this particular period which is high. You can see that there are exactly 5 clocks, 1, 2, 3, 4, 5. This is for the high period. Now if I move to the lower period, you can see that I am coming to the 6th clock, 6, 7, 8, 9, and finally 10. So you can see that both high and low are exactly same. 5 clocks it is high, 5 clocks it is low. So therefore you would get an exactly divide by 10 with a high and a low which are symmetric. And for some applications this may be important. If you are only interested in the frequency, then using the QD output in a BCD mode may not be the right thing to do. Instead you could use this Bi-Quinary mode. So that's the advantage of this particular mode. So in conclusion, let me thank my colleagues Amit, who did all the wiring and all the testing. Especially thanks to Amit, because this was a fairly complicated experiment with a lot of components. And special thanks also to Anil Gawai, who is recording this video and also editing and publishing it. So thank you both Amit and Anil. And thank you students for patiently listening. Thank you.